Let's take a look at our next law in our gas law unit. The next law is called Charles' law. Now, Charles' law is looking at the relationship between temperature and volume. Now, in our Boyle's law example, we looked at the relationship between pressure and volume. So now we're looking at temperature and volume. So what we see here is that a lower temperature results in a smaller volume. So small temperature, small volume. A high temperature results in a high volume or a greater volume. So increasing temperature increases volume. Decreasing temperature decreases volume. So this is what we call a direct relationship, and we represent that with our symbol like this. We have a direct relationship where temperature and volume, if one increases, it will cause the other to increase. And I'll just draw that down, direct relationship. So again, we'll look at the definition of Charles' law, and it says that the temperature of a gas increases, the volume of the gas will proportionally increase, and we provide that our pressure and chemical amount remain consistent. Now again, those are our controlled variables that need to remain consistent in this sort of test. Now we represent Charles' law mathematically as V1 over T1, and I'm just going to record this in a way that's a little bit easier to see. So we have V1 over T1 equals V2 over T2, and again, these are our initial conditions, and these are our final conditions. So because we are dealing with a fraction, this can be a little bit trickier to rearrange than our first law with Boyle's law. So I'm just going to show you how to rearrange this for either solving for any one of these variables here. So if I need to solve for my volume 2, okay, I'm going to, because volume 2 is dividing by T1, volume 2 then means that I would multiply T2 up, and anything that I do to the bottom, I must do to the top, or vice versa. Anything that I do to one side of my reaction, I need to do to the other. So V2 would equal V1 over T1, and because I've multiplied, this should say T2. Since I've multiplied T2 up to the top of my equation here, because this is just a fraction, it's just a divide sign, then I can record T2 on the top of my fraction here. Okay, if I decided to do V1 divided by T1 then times T2 after, you will get mathematically the exact same answer. It's just what you prefer to do using your calculator. Now please note again, if you put this into your calculator, you must put this top portion in brackets because you might get a weird answer if you do not do that. Okay, now if I'm solving for T2, and let me do that in a different color. Let's do that in orange. So if I'm solving for T2, okay, what I see here is that T2 needs to be on the top of a fraction. I can't have 1 over T2 as an answer. So if I was just to simply divide V2 out, that wouldn't work. So my first step is I still need to multiply T2 up, which would result in the same formula here where I have V2 equals V1 times T2. Let me just squish this in here. I just don't like the way this is looking here. So again, we would have the same initial step where we have V1 times T2 over T1. But since I'm solving for T2, now that I see that T2 is on the top of my fraction, I then need to get rid of V1 and T1. So because I'm multiplying V1 times T2, I then divide by V1. And because I'm dividing by T1, I multiply by T1. So then I would get T2 equals V2, and again, I'm going to multiply this guy up and divide this guy down. So I get V2 times T1 over V1. So I completely inverse this expected sort of reaction or this formula in order to solve for T2. So please note that this is sort of a multi-step rearranging, and if you're not familiar with it, you can't solve for T2 on the bottom because that would be 1 over T2. So you want to make sure that if you're solving for T2, this is how you would rearrange that formula. Solving for V2 is a little bit easier, but again, make sure you're using these two formulas to rearrange appropriately. Now let's take a look at an example of what this might look like. Again, I'm just going to underline some words as we go through to make sure that we are making sense of this question. So, in a test of Charles' law, a gas inside of a cylinder with a movable piston is heated to 315 degrees Celsius. The initial volume of the gas in the cylinder is 0.3 liters, at 25 degrees Celsius. What will be the final volume when the temperature is at 315 degrees Celsius? So I'm going to just write down that my V1 is equal to 0.30 liters and that my T1 is equal to 25 degrees Celsius and that my T2 is equal to 315 degrees Celsius and my V2 is what I'm looking for. All right. So I'm going to start out by writing out my equation here. V1 over T1 equals V2 over T2. So that's my initial equation that I know. That is my Charles' law expression. And some things that I need to note is that, and I'm just going to slide this over actually, is that we need to convert all of our units into kelvins. At least our temperature units should be in kelvins. So because of that, I'm going to add 273 kelvins to this, and I'm going to add 273 kelvins to this. So when I add 273 plus 25, I get 298, kelvins. And when I add 273 to 315, I get this equivalent to 588 kelvins. Okay, so because I always should have my units in kelvins when I'm dealing with temperature and gases, I want to convert those units initially. Now, again, because I'm solving for my V2, I need to multiply my T2 up. So my rearranged formula is equal to V2 is V1 times T2 divided by T1. So when I plug these into my equation, I get that my V1 is equal to 0.30 liters times by my second temperature, which is 588 kelvins, divided by my T1, which is 298 kelvins. So because I have an increase in temperature, I do expect to have an increase in volume as well. So when I do my math of 0.3 times 588 divided by 298, I get that this new volume, let's do this in orange, my new volume is equal to 0.591 or 0.59 liters. So we did in fact get an increase in our volume using our formula here. So our theory matched our math, our empirical study matched our theory. So what we see here is we do expect an increase in volume. We get an increase in volume when we have an increase in temperature. That again is called a direct relationship. Now again, I have posted this video on the workspace for Charles' law. This guys, look at how temperature affects the volume using a real life example. So I would like you to take a look at this video once you've gone through the lesson. Another thing you might want to do is you might want to take a look at some more practice questions from your textbook to practice up before moving on to an assignment. All right, good luck.